Hello. Good morning. It's my great pleasure to introduce Professor Hans-Peter Seidel. Professor Seidel is the head of the graphics group at the Max Planck Institute in Germany, and also a professor of the Saarbrücken University. And I especially thank Professor Seidel because he was gracious enough to come especially for this talk. He has a very busy schedule this week, and he's coming just for today and is going back tomorrow. So
absolute record.
Yes, yes. And
even myself was able to do that.
Yes. And so Professor Seidel is going to tell us about his work and the work of his group at the Max Planck Institute, and some things very nice in computer graphics and applied math. Thank you, Professor.
Thanks for the very kind introduction. I would like to thank you all for giving me the opportunity to be here. It's great to be part of this celebration. I think IMPA has done just great. It's widely visible, and I really appreciate the work of the graphics group also. And it's an opportunity for me to come here and to present this work. Well, the general topic is the acquisition of 3D models, which includes geometry, material properties, and to represent all of this in a format that allows you to basically render the data in interactive rates. And this should allow the user to interact with these virtual, quote-unquote, 3D objects, basically in the end in the same way as the user is able to interact with real 3D objects. So here is a little bit high-level motivation. Why do we want to deal with these questions? Well, objects in the real world, they are three-dimensional, they have high resolution, they're perfectly colored and textured, we can interact with them. And of course, there is many applications why we would like to see nothing less on a computer. Think about e-commerce, virtual museums, shared virtual environments, and so forth. And well, this is basically the ingredients that you need to address if you are dealing with these questions. There is a geometry component. You have to somehow acquire the geometry of these objects, simplify it in order to make the amount of data manageable. And then you have appearance of objects, texture of objects. You need to register the information against each other. You need to compress the data, approximate maybe the object or the information by some techniques to reduce the amount of data. And in the end, you want to interactively display this information. So here is one instance of this. This is a bust of Max Planck, the famous physicist, which gave the name to the Max Planck Institute. So this is on the left, you see a photograph of a bust in the lobby of our institute. And we have then digitized the geometry, and this goes to the second picture from the right. And in the end, we've also acquired the material properties. That's a bronze statue, and we're able to now basically render a complete copy of this information. So here is an overview of my talk. After this brief motivation, I want to talk about geometry acquisition and geometry processing, then briefly say something about dealing with textured 3D objects, and in the end talk a little bit, mostly by examples, about so-called BRDF measurements. BRDF is the bidirectional reflectance distribution functions. This is the function that governs how much light coming in from a certain direction is going out in a certain other direction. So if you have information about the BRDF for a certain class of objects, you have then complete information how to render these objects virtually. So we'll start with the geometry acquisition. There is basically 4 instances of the problem. In a sense, the most general instance is that you have measured scattered points, a so-called point cloud without any connectivity information. Another important instance of the problem is that you're dealing with volumetric data. That's the case in medical imaging, where you have samples of a volumetric data set. Then you can also have range scanners. This gives you range images. And you can also have the situation that you have a certain CAD model, say a certain spline surface that you want to convert into another format as say a triangle mesh in order to address a certain graphics hardware very efficiently. So you have also to convert these objects. So basically, given some measured input data of some sorts converted into a single triangle mesh, we're dealing with single triangle meshes here in order to facilitate the rendering on current graphics hardware that are very efficient to deal with triangle meshes. Of course, in a general CAD framework, you're doing a lot of conversions. There's other surface types, splines, for example. But the overhead that's used in these conversions, in the end, everything is converted to triangle meshes. And so one aspect of this work is to try to put in some of the handles that have shown very powerful in the spline context on general triangle meshes. Things like hierarchies, things like multi-resolution analysis. Try to do this directly on a triangle mesh. So this is one example where basically we have taken a test data set consisting of point cloud and then running some algorithm. This was some variant of the rolling ball algorithm for those who are familiar with this to produce a triangulation. This would be the setup in medical imaging where typically you have a certain distance field and you want to reconstruct out of this distance field which has been sampled on a regular grid, an ISO surface describing your object. So one of the standard algorithms for this is the marching cubes algorithm, well understood by now. You build a regular grid, you calculate the values of these distance fields at the grid points, and then you generate a linear approximation to the ISO surface for each grid cell. This algorithm is classic by now, it's well understood. There is certain cases that you have to take care about. You have to avoid holes. All of this is understood. Basically, this is one example. This is one grid cell here. Black could indicate we have a value outside of the surface. The other points would be a value inside the surface. So we know the surface has to pass through this cube here. And you can basically, up to symmetry, consider those instances of the problem here. And the topology of the surface is then tabulated. You have a lookup, and you can stitch the total surface together. Now it's known that marching cubes, the standard marching cubes algorithm, has a severe aliasing effect. So what you see here is an example of an NC milling simulation, and you can see whenever there is sharp corners. So this was a simulation that uses a volumetric representation. If we extract the isosurface, then we have severe aliasing effects, and we're no longer able to sort of judge the quality after running the simple marching cubes algorithm. Another instance here, the MPI logo and some distance field to it processed through the marching cubes algorithm, where you see these artifacts. And well, we have basically tried to address this deficiency in some recent work by proposing two additions to the marching cubes algorithm. One is a change in the representation. The algorithm, the standard algorithm, basically is coordinate dependent, so it works along the coordinate axis. And so we advocate storing the distance field not as a single scalar quantity, but along the x, y, and z directions. And then we basically enhance the algorithm by taking into account first-order derivative information. And that means in those areas where we have sharp features, we add additional sample points lying on the features, and this makes increases the quality of the isosurface reconstruction. And of course, we also produce a little bit more data, but only in those areas where we really have those sharp features. So in a sense, that's an output-sensitive algorithm. Maybe we just look at the picture. So if we have this kind of situation here, then the standard marching cubes algorithm would produce this black point here, while if we store the distances along the coordinate axis, we get the red point here. And well, if we just incorporate this first contribution, taking into account distances stored along the 3 coordinate axis, not just one scalar distance, we see some improvement. So this is a standard benchmark in the field, the so-called fan disk model. In the middle, you would see the result of a isosurface reconstruction using the marching cubes algorithm. On the right, you see a little bit of an improvement, but still it's completely unacceptable in a sense. And this is now where the second ingredient comes in. So what the marching cubes algorithm in these instances, this is a 2D example to just get the idea across. What the standard marching cubes algorithm would produce in this instance, blue is the original surface, black would be the result of the standard marching cubes algorithm. And now if you add these intersection with the coordinate axis, which we are storing explicitly, if you take into account first order derivative information, then you can come up with a reconstruction that's depicted here in red, which is, of course, a first order approximation instead of a 0th order approximation to our solution, and gives a significant improvement in the presence of features. Now, in the surface case, things are a bit more complicated. Basically, what we do, we distinguish between 2 kinds of features. There is corners and there is feature edges. Then you have to do some numerical fitting. We basically use a singular value decomposition on the tangents planes to identify the location of the feature point. And in the end, if you put everything together, we are able to produce a reconstruction that's shown here at the lower right, which is more or less indistinguishable from the original benchmark object. On the upper left, you see the reconstruction that the standard marching cubes algorithm would give you on the same object. On the lower left, we see running the standard algorithm with only the enhanced distance field representation. That's the same image that you saw just before. And on the upper right is also something that's not satisfactory. This is just the taking into account additional first order information, but based on the original representation, which essentially amounts to taking first derivative information at the wrong location. So it's not reasonable to expect a very good result, of course. But if you put the 2 things together, estimate first order information at the right locations, then you can come up with a much improved isosurface reconstruction. Here again, the other example, this milling simulation. And you see that the number of triangles goes slightly up. So now we have 1.2 million triangles in this example instead of 1.1 million triangles for the original algorithm. But you also see that these additional triangles are added exactly in those areas where we have sharp features, and that's, of course, what we want. The third instance was range scanning. So basically, there the problem you have to solve somehow is registration. There is a number of algorithms, such as the iterated closest point algorithm, that allow you to merge data sets to compute a registration after you have a sufficiently good initial value point. If you do this, then you again, at some point, whenever you apply this to technical objects, you will run into the problem of reconstructing sharp features. So we've also addressed this in this setting where we have some reconstruction. Now here at the game, you have to identify feature edges, feature vertices, and then try to move the vertices onto those edges, ridges, or whatever. And we see that there is fairly robust techniques by now to compute such reconstructions, even in the presence of sharp features. Just one example here with different resolutions that illustrate that algorithms these days are able to handle these problems. Now, once you have acquired the geometry, you end up with typically masses of data. And masses of data means typically that's bigger than what you can load into main memory. And this requires that in order to process this, you need some additional post-processing of the geometry. Here is one instance of the problem just to illustrate what we're after. So this is a standard benchmark object that's used by this community, the so-called Stanford Buddha. So on the left, you see the original object made up of roughly 1 million triangles. On the right, you see a simplification consisting of around 5,000 triangles. And at the bottom here, both objects are displayed simultaneously in small size. And at least for those of you sitting in the back of the room, you won't be able to judge if there is any difference between these two objects. But I've reduced the number of polygons that I'm displaying by a factor of roughly 1,000. So, of course, it's clear that in graphics applications, in many applications, it's desirable to have these approximations here. And, well, I like to look at these. There is a slew of algorithms by now. It's a fairly well understood problem, how to approximate triangle meshes with other triangle meshes, where we ideally would like to have the approximation to be a subset of the original object, not just any approximation. We also would like to be these algorithms incremental, so that we don't have just a sequence of approximation, but more or less a continuum of approximations, and that we're able to display the object in an arbitrary resolution depending on the capabilities of our graphics hardware. So most of these algorithms are priority queue driven, and well, basically I like to think of these algorithms as consisting of 3 key ingredients. First of all, there has to be a local simplification operation, how we modify an object locally. For example, we could try to collapse 2 vertices onto each other along an edge. So this would be what is known as a half-edge collapse or an edge collapse, depending on the location of the remaining vertex. Some algorithms try to optimize over the location of the free vertex, or we could take a vertex out and try to fill the hole with other techniques. So that's the first ingredient. The second ingredient, we need some error control on this. One standard error measure is, of course, the Hausdorff distance for such objects. There's other metrics that you can use. And on top of that, we need, as a third ingredient, some sort of a quality matrix that allows us to compute an approximation consisting of well-shaped triangles, or that the triangles are aligned according to the curvature distribution on our original object. We might have color information on top of the geometry that we want to take into account, or we may want to avoid that some of the vertices have excessively high valences, that more and more edges are collapsed into the same vertex. All this can be taken into account by this quality matrix. So basically, the algorithm would, after this choice of local simplification operation and of the global error control, an algorithm would come up with a candidate set of all those vertices that can be collapsed, say, without violating the given error threshold epsilon. And out of this candidate set, we would then pick this vertex that gives us the best shaped triangles. Now, many algorithms that are available these days, and there's also code available, are based on a so-called half-edge collapse. So this is illustrated here. What we're doing here is basically, first we're collapsing the vertex number 6 onto the vertex number 7. And what's nice about this is that in order to invert this process, all we need to store is the geometric location of this vertex number 6, x, y, and z coordinate, and the adjacency information that has been lost after this collapse. So we have to store that vertex number 6 has been connected to vertices number 10, 7, and 2 before the collapse. Then we can reconstruct the original mesh from this mesh here. And in a second step here in this example, I have collapsed vertex 10 onto vertex number 9. And I end up with this approximation here. And as I said, what's nice about this, you can invert this, this process. This is sometimes called a vertex split. So instead of storing the original mesh, I can also store this mesh plus the missing information, the geometric location of the vertex number 6 and the adjacency information. Or I could store this even coarser approximation together with 2 vertex splits. And if I keep going like this, in the end, I end up with a fairly coarse approximation plus this sequence of vertex splits. And then I can try to send to a client from a host first the coarse mesh and then successively these vertex splits. So the client can deal immediately with some coarse approximation of my model and then can, in the background, subsequently build up the model until it has restored completely the original object. Error control, well, I mentioned that the Hausdorff distance is sort of what you might expect. In the context of these applications, you can try to simplify things a little bit by using the one-sided Hausdorff distance, where you basically measure the distance of the original vertices to the approximation. This is due to the fact that in many input data, you only have the location of the original vertices. You don't have a priori a triangle mesh, so in a sense, first-class information is just the location of the vertices, and that's why, in some sense, you should only measure the distance of the original vertices to your approximating surface and nothing else. And quality metrics, the third ingredient, well, they are used to control the geometry, well-shaped triangles, bounds on the normals, the topology, no excessively high valences, or we could try to minimize, for example, texture distortion by these attributes. So I think I don't want to go into details here. This is an example. On the left, you have a sort of a regular mesh. This is something you would like to have, having average valence 6, not just on the average, but more or less everywhere, versus on the right, where you have some vertices that have very low valences and some vertices, as shown here, with very high valences, which, of course, implies that you will have all kinds of numerical problems in post-processing this kind of triangle mesh. And here is finally an example where we have taken into account color. You see here we have the number of triangles decreased by a fair amount, and still sort of since we're taking into account color, you may even argue that this is a better visual representation. And an important aspect in many applications is, of course, that you are able to deal with adaptive refinement, that you're able to modify your surface locally whenever need be, if you think about animation and so forth. So let's look at a couple of examples that come out of this mesh decimation. This is a test object that has been, where the number of triangles has been reduced significantly. This is an object that we're using in the context of texture mapping. So here later on you'll see another instance of this, but then with as a textured object. Then the next thing, I'm not going to talk about smoothing operators here because there will be another talk on Friday, I think, by Gabriel Taubin, where he will go into detail about this. Now, one game you can play is that you try to combine mesh decimation with smoothing. And if you do this, this allows you to come up with a multi-resolution modeling paradigm directly on the data structure of a triangle mesh. So basically what we're doing here is we're starting with an object A, then we're running our favorite mesh decimation algorithm, and we organize the algorithm in such a way that vertices are removed more or less evenly over the object. And we don't just run one step of the algorithm, but we run the algorithm until we have reduced the number of vertices by a factor of 2. So the object B prime, you could call this, has about half as many vertices as the original object A. And then on top of this piecewise linear approximation, we run a certain smoothing operator to produce a smooth variant of this coarse approximation. And this is called B here. Then we do the same. We keep continuing, reduce the number of vertices by a factor of 2, and produce a smoothed version of this until we end up with some coarse approximation and a smoothed version of this, which is called here D. And then we can just re-represent the original object as this smoothed coarse version D plus these differences. And we can try to use this in surface editing. And I want to show you one example here. Editing now means we change the coarse approximation. For example, we move the head. We change this to D prime and then subsequently add back the detail that we had just deleted. So this is an example here that we did in a project with a car company. So the goal here was this is a mesh consisting of some 100,000 polygons. The reduction algorithm took care to respect this feature on the hood. And we can now edit the hood, but we're preserving sort of the characteristic shape of this car brand. Another example here that I mentioned already before is a progressive transmission. So this is the Max Planck bus. And now instead of transmitting the information sequentially, we can also do this progressively in the middle. So what we do here and what you see in the middle, we first broadcast a coarse approximation of the object and then subsequently add in all those vertex splits to produce the final result. You can think of the left model as providing a timeline for this. On the right, we see only the vertices. And you see that after about half the information has arrived, for the visual observer, at least on this resolution, there is no difference in the object visible anymore. And so you may well start to interact with your object after about half the data or even less has arrived. You don't have to wait for the full data set to be on your client. So this is important whenever you talk about limited network channels. Another application of this, of course, that you're able now with these techniques to implement 3D graphics on fairly simple platforms such as this Palm Pilot, where you simply use some sort of an approximation that's small enough to allow interactive behavior even on such a device. And finally here an example taken from industrial design. So we see on the left a reduced triangle mesh of a full car that has been obtained by merging 8 different scans with together with a CAD model. And you see that the data reduction has been carried out in such a way that we have only a small amount of vertices in fairly flat regions, while we are preserving a lot of detail in the interesting regions where there's feature lines. And well, once you have such a reduced triangle mesh representation, you can then, for example, inspect the visual quality of these objects. This is so-called reflection lines. So this is a simulation of what is being used in the car industry, where people have big holes with parallel light sources on the ceiling, and they drive the car into the building and look at the reflections that these light patterns have on the car. Up to, say, 5 years ago, there was many papers written on analytically computing these reflection lines on certain surface descriptions, such as spline surfaces, bicubic splines, so forth. And these techniques were used. Nowadays, this is always done throughout the car industry using high-level quality graphics hardware, for example, a Powerwall, a stereo display. And there, people are always dealing with some polygonal model. It's essential to have low polygon count, otherwise you cannot access these devices in interactive frame rates. And then, of course, your mesh decimation algorithm has to take care that the reduction is done in a way that the triangles are aligned to the curvature behavior. Otherwise, you cannot hope for getting the right reflection lines. But this can be incorporated in the algorithm by means of this quality measure predicate that are introduced as my third ingredient. And then, of course, you can all do all kinds of fancy things like computing a light simulation here. Here we put the car outside of a virtual instance of the car outside our institute. That's actually quite ambitious to compute a daylight simulation of a car, even these days. But this can be done with these techniques. So basically, up to now, I have focused on the geometry part. Now, real 3D objects, they consist of geometry, but they have also surface properties, like this desk, for example. It has a texture, it's a wooden desk, but it also has reflectance properties. It reflects light coming in from a certain direction in other directions. And the kind of behavior, if you perceive this as being a diffuse, somewhat diffuse object or a highly specular object, may actually depend on where you're sitting in the room. So people that are sitting in the front will perceive this as a highly, almost mirror-like object, while people sitting higher up may have the impression of a diffuse object. And these material properties have also to be acquired if you want to do if you want to be able to realistically interact with these objects. So first I'll start with texture. This is an area where people at IMPA are also quite active, and just had a chance to look through some of the latest work. So this is an area where we may actually have a chance for maybe collaborating in the future. So what you see here, just to make my point, is we have a geometry of a certain object, and then we have texture data typically coming in from certain photographs taken with a digital camera. And then, of course, the first step is that you have to register these information against each other. There is all kinds of techniques. Sometimes you can, of course, try to use markers. That's not always possible, so you also want to have techniques that allow you to register the information without any additional markers. So we have suggested a silhouette-based approach where we take the silhouettes of the object. We speed up the algorithm using graphics hardware. We basically render both silhouettes in different colors and then let the graphics hardware do the actual work. I'll show you just one example here, where sort of we run this algorithm a couple of times to avoid local minima. We also do this in a hierarchical fashion, first a low resolution, then a high resolution object, and this allows us to do the registration. You see here, down here, and I'll come back to this later, a flaw. This is due to the fact that even with taking 12 shots of the object, we have missed a certain part of the object. We don't have any texture information for a certain part of the object. So this is something that whatever 3D photographic equipment you may buy these days, acquisition planning is basically unsolved. So that's one project we're working on with Minolta. Minolta scanners are sort of one of the standard hardware devices that are used for this to improve on this acquisition planning. Then we stitch together the texture by basically using projective texture mapping. For each triangle, you try to identify the image that's best for this triangle, and then you blend the textures across the borders using standard alpha blending in graphics hardware. And as one example, we have this object here, and you see that the results are reasonable. You see there are slightly different colors, so this is information that comes from, if you look at the wheels, that comes from different scans. But you see that the fine grain wooden structure is well preserved even across, like this is a boundary between two scans, is very well preserved across the scans. And the defect that I mentioned is visible right here at the bottom. This is a portion of the object where no texture data have been acquired during the taking the photographic images. And just to illustrate how well the wooden texture is preserved with this, in a sense, fairly simple technique of using silhouettes to do the registration. Now the final ingredient, once we have texture, is also to incorporate the reflectance of light into our framework. And just to illustrate again what this is about, so we have this plastic duck. There is many copies now all over our lab. Also in Italy, people are using it, and it's just a simple object, and you can do all kinds of fancy stuff, and it doesn't cost any money. So this would be pure geometry, the first part of the talk. Here we have geometry plus texture, which gives you a fairly good impression of the object, but you're not able to change the lighting conditions. As soon as you would want to change the lighting conditions, you would get a different object, and this would not be captured by the representation that we have up to now. So one could try to compute a single average reflectance function on this object. This would be the result shown here, where now we can change the lighting conditions. We could combine this with texture, but still this would, of course, not give a very realistic setting, because if there's different materials, then the reflection of light will be quite different at different parts of the objects. And, well, in the end, what you see here, this is now the result of geometry plus a spatially varying reflectance function, where we have different reflectance functions across the object. They are clustered, so there is, I think here it's 6 clusters. And then we even have this fine detail, for example, above the eye. So some child has scratched the object there. And we have a different, not just a different color, but also a different reflectance distribution function in these instances. And this can also be captured now in this framework. And basically, the amount of data that you need to store for this reflectance distribution function is, for each of the clusters, 6 floating point values. So it's a fairly compact representation that allows you to basically do everything you want to do with the object. So I'll be very brief here. Basically, we're collecting for each point on the surface certain data. Then we fit a certain reflection model to the data. Then we run some variant of Lloyd iteration to separate the basic materials. And then in the end, represent each point on the surface in the basis that we get by this decomposition into cluster, and thus are able to have a spatially varying BRDF at each point on the surface. We have built a lab for this. I've just learned that a similar effort is underway here. So there is a 3D scanner. There is a set of digital cameras for texture acquisition, and we're using digital cameras for BRDF measurements. In order to make this process work, you need fairly clear-cut lighting conditions. So we have a very good approximation to a point light source in this room. You have dark carpet all over the room. There is calibration targets, the checkerboard. There is this metal spheres that you see here that are used for calibration. So it took quite an effort to set up this lab, but only then makes it sense to address sort of the issue of digitizing high-quality 3D objects if you have this kind of setup. And of course, in future research, one of the goals will be to get rid of all the constraints more and more, that ideally you would like to have a small 3D camera that you can take photographs around the room and then reproduce whatever you see. Then we do this fitting result. we fit this reflectance function and then do the clustering, which I just illustrate here. So second comes this cluster here. Then we have the area around the eyes. We have the eyes. So this is the last cluster now. And at this point, we have all the clusters, but the object still doesn't look identical to the real object because, for example, we don't have these scratches. And this can then be incorporated as a final step where we represent, for each point on the surface, the reflectance function in the basis given by these clusters and do a refit to our data, and then we get this representation here. Two more examples to wrap up my presentation. This is an image here of a set of angles on the left. On the right, you see the reproduction. So we go through the whole process. You see some subtle differences. The highlights are slightly bigger at those feet, also at the wings. But overall, it's a fairly good reproduction, and also if you look at the texture around the hair, this is fairly well preserved here. And of course, the benefit now is that you don't just have a photograph, but you have a 3D representation. You can relight this object, and you can inspect it from all sides. And you see the different reflectance properties across different parts of these objects, at the wings or in the hair, or there is this band around the hair that has a very high reflectivity in contrast to other parts. And finally, this bust of Max Planck again that I started with. So on the left is a geometry reconstruction. On the right, we now see geometry plus material properties. And now you can also relight this object or introspect it from different locations. I think there is 4 clusters in this bronze object. And what comes up here now at the bottom of the backside is the inscription of the artist. And this is not captured in the geometry at all. So the geometry reduction basically threw this away. It never was really present in the data, but by taking into account this reflectance properties, we can now reconstruct this inscription, which originally, of course, is visible in the geometry as well. So you can also use the material properties to reconstruct the geometry using the things as normal maps if you want to do this, but that's also room for future work. So here's an acknowledgement to some of the students and former co-workers that have been involved with this work. And of course, I thank you for your attendance and wish you a happy birthday, IMPA. Thank you very much.
Should I repeat the question? When you mentioned the method to register texture by using silhouettes, do you assume that you have already acquired the 3D geometry, or you do both at the same time?
Here we did assume that we have acquired already full 3D geometry. A variant of this, it turned out that the geometry was not necessarily wrong, but it was the error margin in the geometry was far higher than the error margin in the texture that came out as a result of this. So we also used this in the end to change the geometry. But the way I presented the algorithm and the way it was originally designed, we had complete geometry information, so the registration of the different geometry parts was already completed, and then we registered the complete geometry against the different images.
Thank you.
Before we close, I'd like to make an announcement. There will be a group photo today at 12:10 on the terrace on the 3rd floor. So ask everybody to go there at this time. And so to close, I would really like to thank Professor Hans-Peter Seidel for the excellent talk and for coming here to the commemoration of the 50 years of IMPA. Okay, thank you.
Thanks.